So up to now, we've dealt with some arithmetic sequence and series and geometric sequence and series. We've also looked at infinite geometric series. And we're going to look at other infinite series other than geometric series. So an infinite series either converges or diverges. So an infinite sum converges or diverges. So converging means that it has a finite sum. Diverging means it has an infinite sum. So some geometric series diverge and some converge. And so for an infinite series to have a finite sum or converging, it has to have some properties. So let's take a look at some of these properties. So this is an infinite geometric series. The R value is equal to 1.2, so we're multiplying by 1.2 each time. So every term is getting bigger. So we're adding an infinite number of terms that are getting bigger and bigger. This must diverge. It must have an infinite sum. Here we have a geometric series. Again, we're going to test this. So R is equal to 3 over 4. And this series is infinite, and it is getting smaller and smaller each step. And it's getting smaller fast enough so that it has a finite sum. So this happens to add up to 800, so we say it converges. This third one is not a geometric series. Okay, this says the denominator is being squared. Okay, this is going exponentially, this is going by just squares. But this one happens to be getting smaller and smaller and smaller. So 1 squared, 2 squared, 3 squared, 4 squared. The denominator is getting bigger, so each term is getting smaller, and eventually will go to 0. And this happens to be going to 0 fast enough for it to converge. Okay, so this is a converging infinite series, but this is not a geometric series. So one thing about geometric series is that they get small enough fast enough so that they all will converge because the denominator is exponential. Sometimes the denominator is not quite as powerful as the exponent, so in this case it's a square, but it's still going to, this denominator is getting big enough fast enough for the term to go to 0 fast enough for it to converge. So there's some criteria that we have to observe before we can consider a series to converge. And the criteria that we must meet, this is not the only criteria, but we have to meet this criteria, is that the terms must get smaller, not just smaller, but they must get smaller to 0. Okay, so they must converge to 0. So if the terms of the sequence, the Tn, goes to 0 as n goes to 0, that means that it's possible for it to converge. So this last question here is that if the terms of sequence goes to 0, does that mean that series always converges? Well, the answer to that would be no, because there are some series where the terms go to 0, so we're adding up terms that eventually go to 0, but we're adding an infinite number of terms, and because it doesn't go to 0 fast enough, the series does not converge. So we'll take a look at a couple of those.